So it is my great pleasure to introduce the next speaker, Professor Minhyong Kim from the University of Oxford. After his getting PhD at the Yale University, he successfully got the position of professors at the University of Arizona and Purdue University, and then University College London, and now the University of Oxford. And he's one of the leading researchers in the area of arithmetic algebraic geometry. And among other things, his most famous work so far is his brand new approach to various problems in Diophantine geometry by using the theory of arithmetic fundamental groups in the periodic context. And here I'm happy to tell you that part of this work was done during his stay in Kyoto as a visiting professor at RIMS. Now, today's title is Reciprocity Laws, Diophantine Equations, and Fundamental Groups.
Thank you very much. Is this working okay?
Oh, I see. Okay. Thank you very much for the introduction and the invitation to come here. It's wonderful to visit Kyoto, which is always a great source of ideas. Professor Tamaga already mentioned that much of the work I'm describing today was done here. And then I ran out of ideas for many years because of not coming to Kyoto. I'm trying to get some more even during this short visit. I was told that it should be something like a colloquium lecture for non-experts, including non-number theorists, and I hope I put in some effort to make it like this. And in particular, I wasn't sure. So there are many objects mentioned in the title here, but I wasn't sure how to express what the main point is. What is it I'm trying to study? Because I don't know most of the time what I'm trying to study with these things. For the sake of the lecture today, I thought I'd focus on the case of what I might call arithmetic fields of an arithmetic nature, which again we can use in a very vague way, but whatever one might mean in general, in any case, you're always going to mean things like the fields of rational numbers, right? Or fields of algebraic number fields, which are finite field extensions of the rational number. One might mean other things as well, for example, finitely generated fields, but for now, I'll focus on this case and I'll say what I'm going to describe in today's lecture is just some, roughly speaking, digressions surrounding the study of arithmetic fields of this sort. Now, algebraic number fields, if we're being very concrete about it, we can view them as just a vector space Q to the D with some nice multiplicative structures. So these are finite field extensions of Q. So for example, here are some examples, classical examples, as well as that last one down there. That's actually a very interesting field for reasons known only to number theorists. Or you can have higher dimensional examples like this. So roughly speaking, these are the arithmetic fields that I'm talking about today. So about these, I'm going to pose just one brief question, namely the problem of how to classify such things. And I'm going to say almost nothing about actual classification, but just mention that this problem of classification is somewhere in the background as motivating the kind of even very concrete investigations that we'd like to do. And I guess one general remark is that this classification is very hard and very little is known. But you could also ask why we should classify such things. And I guess what I wanted to say is states that the classification problem is there as an inspiration for a lot of mathematics, but the question of why we should classify is also there. And I'm not going to give any kind of an answer to that either, because the answer is too long. I think there is an answer, but I certainly can't say it in any coherent way that would fit into a lecture. But I'll mention that this question of why is also in the background together with the problem of Nevertheless, even though the problem of classification is in some sense wide open, I'll mention that there are some related results of this sort. Right? I'm just mentioning names here without even telling you what the results are. So for example, D here refers to the degree of the field extension, that is the dimension as the rational vector space. And I think it was Gauss that classified quadratic fields, is that right? I'm always confused by this. Fields of dimension 2, degree 2, I think was classified by Gauss. Then, after more than 100 years, Davenport and Heilbronn had this theorem for degree 3 fields, and then several decades after that, recently Manjul-Vargava, in some sense, classified fields of degree 4 and 5. But here, these classification theorems, I just mentioned this just to say that these results really are not of the right sort. In many different senses, but in particular, if you look at these results for degree 3 and degree 4 and 5, they don't come anywhere near to actually classifying. But all they do is they count number fields of a given discriminant, for example, in some asymptotic fashion. As I said, I'm not going to even state the results, but I will mention that these great theorems, like Vargava's theorems in recent decades, they are only scratching the surface of classification, indicating how difficult these kind of problems are. And there are other senses in which these are really not the kind of classification theorem of the sort that I'm interested in myself. So instead, I'll move on to a brief description of the classification of the sort that I'm trying to understand myself, and I think other people here are also trying to understand. So in order to do that, I'm taking a mildly historical approach without being anything like a historian myself. And I'll mention that maybe the first result classification theorems of the right sort are what constitute Galois theory. And we all know what this is, but I'll just remind you anyways. So I used to think that putting pictures into lectures was a bit of a distraction. But lately I've been feeling like for colloquium lectures it's kind of nice to get a historical perspective by seeing what the people look like. So I put some pictures into these lectures, So that's Galois. So what does Galois theory do? From the point of view of classification, what it actually does is something like this. Let's see, I guess this is the point. It assumes that there's a field that you already understand. A field extension that you already understand. And we also put some condition on it, like that the field extension is Galois. Meaning what? That it has a lot of, the maximum number of automorphisms. If there are as many automorphisms as this dimension, it's a sort of elementary field theory to see that there can't be more automorphisms than the dimension. If it actually has that maximum number, we say it's Galois. So what we do in Galois theory, we assume that a field of this sort is given, then the main theorem classifies the subfields of F. So that's what it is. So it's a great theorem, but there's a way in which it's unsatisfactory. Why? Because it's kind of a top-down classification. You assume that some big F is given, right? And then it says, well, subgroups of the Galois groups correspond to sub-extensions. Right, but nevertheless, of course, this theorem was a big advance. And that's the first classification theorem of the right sort that in the sense that I was describing earlier. Was still unsatisfactory as it is. Now, the second part of this more or less historical progression, I'll describe class field theory. No? And this is a photograph of Takagi, who was one of the founders of class field theory, and another founder was Emil Artin. Together we refer to class field theory as often the Artin-Takagi class field theory. Or should it be Takagi-Artin class field? Anyways, so what did they do in their work? So this was a bottom-up classification, or it's an attempt to give a bottom-up classification. Meaning what? Here you start with F, so for example F could be Q itself, right? And then you make some attempt to see what kind of case can be built out of F further. So in this sense, it's much more of a constructive approach than assuming something is given at the top and then try to see what lies under it. So here you start from the bottom and you try to build up. Furthermore, the idea generally in class field theory is that these k's that lie above f should be classified intrinsically in terms of f in some suitable sense. So here I'll go back to this picture. So if you're given f, you're trying to classify the possible k's that lie above f, and somehow you should be able to describe the possibilities intrinsically in terms of f. And this is the idea, the program of class field theory in many ways. Now, what we mean by intrinsically, as many other things I'm saying right now, one can take in a very vague sense. So you shouldn't be too rigid about what you mean here by intrinsically. Nevertheless, there is a guiding principle, namely that the motivation actually does. A lot of the motivation for what this intrinsically might mean does come from topology. Namely, the situation where if you have a connected space, for example, then the coverings of X can be classified by finite coverings, for example, can be classified by finite index subgroups of the topological fundamental group of X. And this, of course, in some sense is an intrinsic invariant of X that in a lot of cases, for example, if you're given a CW complex or something, you can compute it using combinatorial data. So in that sense, this kind of intrinsic invariant in topology allows us to classify the covering space of things that lie above X. And class field theory also attempts to do something similar by trying to find an arithmetic substitute for this kind of thing. So what does the Artin-Takagi theorem theory do? In particular, by the way, I often make mistakes when I state theorems of class field theory. So fortunately, there are many experts in the audience to correct me. So Takagi in particular defined an actual profinite topological group. So here this limit means that it's an inverse limit. It's a system of elements inside finite groups. Right? So turning this into a profinite topological group. And he defined a topological group that actually does something very similar to what the fundamental group does. Namely, the open subgroups of this topological group end up to being in correspondence with the finite extensions of F, except they're the finite abelian extensions. This was the limitation of the theory here comparing to topology. You don't get all extensions, but just the finite abelian extension. So it is possible to have a substitute for topological fundamental group, except it's not quite a substitute, because you can only build up finite abelian. Artin carried this a little bit further. So for years, I was puzzled about what the role of the two different people were. And I think the way I formulated it here is correct. Takagi wrote down this topological group whose open subgroups correspond to finite abelian extension. Then Artin actually proved that there's a canonical isomorphism from this group. So what is this thing here? You take an algebraic closure of F, and take the Galois group, all the automorphisms of that field that except, then take the abelianization. So this is the abelian Galois group of F, absolute abelian Galois group of F. And Artin defined an isomorphism between this topological group and this abelianized Galois group. So this was called the Artin reciprocity. So together, this constitutes the class field theory in the sense of Artin and Takagi. Right. So to repeat what I said already, so in some sense, whatever these things are, actually, sorry, maybe I'll give just two examples first. So for example, if F is Q, then these levels of the group that appear in the inverse system are just the invertible elements in Z mod M. So this subgroup, group of invertible elements inside this ring Z mod M. And if F happens to be a field like Q with the square root of I minus 1 adjoint, then the levels look like this. Take inverse limit of these things. So there, again, I hope that even this picture indicates you some sense in which these groups can be built intrinsically out of the field. This is the flavor of the class field theory in all situations. Nevertheless, as I said already, and as people have been struggling with for a long time, we can't really seem to give a similar description with the abelian removed. If you want to describe the whole Galois group, we can't quite do it as yet, and it's a very active area of research. In different forms, this might be what's called, but in different forms, people call this non-abelian class field theory, or attempts to replicate this picture or generalize the Artin-Takagi picture to get the whole Galois group, or at least some large non-abelian portions of this that go beyond the abelianization. The most famous case of this is probably what's called the Langlands program. In the Langlands program, you try to address this problem of describing this group by linearizing the problem. That is to say, instead of looking at the group itself, you try to classify the representations of the group. And the representations of this group are supposed to be classified in terms of something called automorphic forms attached. So special functions on complex domains that are somehow canonically built out of it are supposed to give you a classification of the linear representations of the Galois group. And that's one version of non-abelian class field theory. People that is really one of the most active areas of number theory in the present day. Here's a picture of Langlands. Relatively recent picture. Yeah, but now I'm not going to say anything about non-abelian class field theory in this sense, even though it does still inspire a good deal of what I think about, and pretty much what all number theories are somehow affected by this program in some form or another. Nevertheless, today I'm not going to say anything about it for lack of competence, among other things. Instead, I'm going to continue this somewhat semi-historical survey with a little bit of a digression that moves away from number fields for a second, and instead mentions these non-Archimedean fields that somehow intrude upon our study of these arithmetic fields. They're not strictly arithmetic fields in the sense that we normally think about it. They're not like Q or number fields or finitely generated fields, but they arise in a natural way when trying to study arithmetic fields. There's a picture of Kurt Hünzel, who I guess is the first person to study these kinds of things. So here's a picture. You take, normally this is the way one thinks about it, you take the rational numbers, and if you study mathematics in the usual fashion, the rational numbers will become a subfield of the real number. Right? But then it turns out that you can put it into other complete fields, the two-adding numbers, the three-adding numbers, the five-adding numbers, and so forth. Right? And so you view some Q as lying at the intersection of all these different complete fields. And this one is Archimedean, and all the rest are non-Archimedean. You can do something very similar for algebraic number fields as well, put them into various completions and form a picture very similar to this, but I'm not going to spell out. So there are many things in number theory that you do with these different completions. But the aspect that I'm going to mention first of all is this relation to class field theory. This seems to be due to Hasse, this connection between non-Archimedean fields and class field theory. Hasse did many things with these non-Archimedean fields, but among them, class field theory. So what did he do? What he did was he took one of these non-Archimedean fields, right, and took the group of non-zero elements inside the field, right, and then he connected it to Galois theorem. So this is the so-called local reciprocity map that takes the non-zero elements inside one of these complete fields and puts it to define an injective homomorphism, which is essentially canonical. There's a little choice of normalization that's involved in the definition. Essentially canonically, you can put it into the Galois group of this field FV itself, again abelianized. To abelianize it, this is called the local reciprocity map that belongs to local class field theory. But these Galois groups, in fact, all sit inside, you can put them inside the Galois group of the number field F. Remember, to restate, we're actually interested in these algebraic number fields, right? We've completed it to one of these non-Archimedean fields. The non-zero elements, the multiplicative group of the non-Archimedean field, maps into, this complete field, maps into an abelian Galois group of that field itself. But by embedding F bar into F V bar, you can also get an inclusion of Galois groups of this sort. So what ends up happening is that all these non-Archimedean fields actually come together inside this big Galois group here. And this is a very significant picture, I think, from many points of view. That's worth emphasizing. So here's a picture for the case of Q. So here you have the absolute Galois group of Q, abelianized. But then all these different non-Archimedean fields come together inside this big group. Which, the reason I'm emphasizing this, especially for young students, is that when you first study these completions of the rational numbers, sometimes you're given the impression that they all form different, completely different universes that have nothing to do with each other. Yeah? And they only intersect in the rationals or algebraic numbers or something like that. And that's true from a certain point of view, but from the point of view of class field theory, that's not true at all. They all come together inside this Galois group. And help us to understand this group, and they interact in complicated ways inside this group. And that's part of the reason why they are natural in some sense from the point of view of studying arithmetic fields. This group is very natural, as these are the symmetry groups of these arithmetic fields. And then it somehow naturally contains all these other complete fields, which also explains the profinite nature of their topology, because this picture deserves much more emphasis when we're studying algebraic number theory compared to the picture where these are all separated. I'll also mention that these maps can all be put together. So here I've already once again change the context to the case of a general field. They can all be put together to define something called an idyllic reciprocity map. I guess I should have mentioned this first, but so this is essentially a product of all these guys. So these idels are a product of all these non-Archimedean fields for F, for the completion F, and then all these local reciprocity maps can be put together to take a product of all these things and get an idyllic global reciprocity. This abelianized Galois group. And all of this, so up to here was done by Hasse, but this idyllic reciprocity map seems to have been first defined by Chevalier. Here's a puzzle. Who are these two gentlemen back here? Anybody knows? Sorry?
Do you know?
I know, yes. Nobody knows. One of them was in Kyoto for sure. Akizuki, that's right. The gentleman on the left is Akizuki. And the gentleman on the right, I don't know him. Well, I guess his name was, suddenly the name escapes me. Kobori, maybe? Somebody like that. I don't know exactly where they took this photo. Akizuki was definitely here in Kyoto, I think. Okay. Anyways, so this idyllic reciprocity map was yet another version of class field theory. Right. Now, but if I go back, if we continue this discussion of non-Archimedean fields, it's of course well known that another way in which it arises, and maybe it first arose in the work of Hasse as well, was in the study of Diophantine equations, not in the study of Galois groups per se, although the connection comes up very quickly, but nevertheless, it probably arose first in the study of equations. So what do I mean by that? So for example, the square root of -1, which doesn't lie inside the reals, lie inside all these other completions. So x squared plus 1 equals 0 can be solved inside these other fields, although they can't be solved inside the reals. So this is the general statement. This is the square root of minus 1 is inside QP for all p congruent to 1 mod 4, for example. So this is the kind of equation solving you can do with these non-Archimedean completions. And this statement already tells you that they must contain some kind of insight about solving equations that's not accessible in the reals. The reason, from an arithmetic viewpoint, that these are very useful is because this QP, in a sense, forms a bridge between solutions inside finite rings of this sort and solutions in Q. So this is the picture. So you can put Q inside one of these completions, but inside here there's a subring of those things. If you take the metric point of view, this is the subring of elements that have absolute value less than or equal to 1. But then these have all these finite quotient rings that multiply, for example, FP. So you can take solutions inside these finite rings, which are much easier to analyze than solutions in Q. And consider, say, sometimes lift those solutions to ZP, then that gives you solutions in QP. Somehow are supposed to come together to give you insight on solutions in Q. So this is more or less the way in which we usually introduce these non-Archimedean fields in undergraduate number theory classes via this question of solving equation in connection with this question of solving equation. Here, for example, is one of the most the first deep theorem regarding these completions. It's sometimes called the Hassen-Minkowski theorem. I didn't prepare a picture of Minkowski. But what it says is that for equations of this sort, so this seems like a very simple equation, but still it's quite a deep theorem in its own way, this theorem, that if you take an equation like ax squared plus by squared equals c, and you want to solve it inside the number field f, then in fact, the solution exists inside the number field if and only if there's a solution inside all these completions. So that's actually quite an interesting theorem, and I think, as I said, the first actually deep theorem concerning that applies these non-Archimedean fields. And this turns out to be quite an effective theorem as well. So for example, I'll just state it in the case of Q. When f equals Q, and you want to know whether or not one of these equations has a solution, right? And you just need to check it for R. You just need to check if it has real solutions, and QP solutions for all P's dividing twice of A, B, C. So it says for all V, but you don't actually need to check for all V. Most of the V's turn out to be automatic. And it suffices to check it for a finite collection, and for example, when f equals Q, for reals and p-adics for P dividing these coefficients and P equals 2. And whether or not there's a solution inside these fields, there's again a straightforward criterion. So this is these things called Hilbert symbols. You don't have to know what they are, but they are readily computable given these A, B, C. They are plus or minus ones. Plus ones or minus ones, all of them, right? And they can be easily computed. You're given these numbers A, B, C, so that you get a very effectively checkable criterion for whether or not this equation has a solution. So this is, as I said, one of the first deep theorems connecting non-Archimedean fields and number fields, what are also called global fields in this. Now, this theorem has inspired a lot of number theory. In particular, people have attempted many different kinds of generalizations. What kinds? Well, you could start with a rather general system of equations, a rather general variety defined over a number field, right? And then we're just expressing the fact that the f rational points, that the solutions inside your number field, can be embedded inside the product of solutions inside all these completions. So this is the so-called ring of Adel, which is essentially a product of all these V's. So given any f solution to the equation, you get a bunch of fv solutions simply because f lies inside all of these completions. So as a result, for example, if it doesn't have, if the equation doesn't have any adelic solution, for example, if it doesn't have FV solution for any given V, right, then of course it can't have any F solution. So this is the typical application, or easy application, so to speak, to say that an equation has no solutions inside Q because it doesn't have a solution inside R, or it doesn't have a solutions inside the two addict. So this is these are the easy applications that arise from these inclusions. But sometimes, as in the Hasselmann-Koski theorem, the converse is also true. And this requires considerably more number theory. That is to say, sometimes it happens that when this is non-empty, it also implies that the F rational solutions, set of F rational solution is non-empty. This doesn't happen too often, but this is exactly what happened in the case of this equation, ax squared plus by squared equals 3. That the non-emptiness of this set sometimes allows us to conclude the non-emptiness of the much smaller set. Whenever this happens for some class of variety, we say that the Hasse principle holds. This is called the Hasse principle. This statement for some class of equations that says that if this is non-empty, this smaller set is also non-empty. But as I said, it's very rare. It's only for a very special class of variety, a naive statement. Existence of some solutions inside say R and QP for all QP implies the existence of a rational function. Nevertheless, it's a fascinating enough phenomenon to have deserved its own name. Well, but because it's such a rare phenomenon, what people have tried to do, many people, including me, is we've tried to refine this Hasse principle. What kind of refinement am I referring to? Well, the general picture, remember, is still this. The F rational points of the variety always lie inside the adelic point, the product of the local points. So you could ask, well, sometimes when this is non-empty, well, if this is empty, this is empty. That was the easy implication we stated. Rarely, when this is non-empty, this is also non-empty. That's when the Hasse principle holds. But still, even in greater generality, we could ask whether or not we can locate the way these points, F rational points, sit inside the adelic point. And that's a refined question you can ask that goes beyond the Hasse principle. So even with the Hasselmann-Koski theorem, by the way, when you teach it in an undergraduate course, even students always ask this question. They ask, but it's not, the theorem isn't actually saying that any adelic point is actually a global point. It's just saying that if there is an adelic point, then there also is a global point. It doesn't tell you which of the adelic points are global points. So you could ask this more refined question. Can we recognize this in some way? And when we ask the question in that form, the question generalizes to other equations as well. Why not? Maybe there are better theorems that allow us to recognize the existence of global points, even when the Hasse principle fails. Okay, so with that question in mind, let's recall, we go back to this simple equation, ax squared plus by squared equals c. And I'll simplify further by assuming that there already is a rational point. We can generalize beyond this class with more work, but I'm not, in order to reduce technicalities, I'm going to just assume that there is a rational point and also that the points at infinity are rational. So there's a minor further technical condition. So when you put all this together in a simple case, or that this factorizes, that's another way of putting it, then the variety defined by this equation just turns out to be the so-called multiplicative group, in this case, so that the global points of this variety are just the non-zero elements inside F. And the same for the local points. Inside one of these completions, the points can be just identified with non-zero elements inside F. So this question of locating the global points inside the adelic points, sorry, I've inconsistently used stars somewhere and cross other places. They should all be the same. Anyway, the problem of locating the global points of this x, in this case, inside the adelic points. It's just a problem of locating the field inside the idel. That's what it becomes in this case. And in some sense, this problem has already been solved. Why? Well, this is where the so-called reciprocity law comes in. That is to say, remember, we had this idelic reciprocity map defined by Chevrolet that goes from idels to the abelian Galois group of the field. And there's, I didn't state it before, but the class field theory includes a so-called reciprocity law for this map, which generalizes the Gauss reciprocity law and Hilbert reciprocity and all previous reciprocity laws that people cooked up in the 19th century. What it says is actually that this map, from the idels to the abelianized Galois group, actually kills the field sitting inside the idel. This composed map is zero. So this kind of statement, when you formulate it correctly, as I said, it includes quadratic reciprocity and all the concrete reciprocity laws, and it's a great generalization of it. But from our point of view, the point I'm stressing is that the reciprocity law itself, therefore, gives us a defining equation for the way the field sits inside the idel. So this is a very simple observation, but for me, it took me a long time to appreciate this in some way. That somehow, you can write down, in some sense, an equation on the set of idels whose zero set exactly contains the so-called principal idel. It tells you how F star sits inside the idels. It's not exact, although I used the word exact, but unfortunately the kernel of the reciprocity law isn't exactly this, but it does give us a very strong constraint of the locus of the global points of the multiplicative group inside the adelic point. Except it's an equation that takes values in a group. So that's the interesting part of this story. That somehow it's not an equation, or it's not a polynomial equation, or an analytic equation of any obvious sort, but it's an equation with values in a group. But subject to that generalization, it does, in some sense, give us something of a solution to the problem of identifying the global points inside. And this is what we'd like to generalize to a kind of non-abelian reciprocity law of some sort. What sort? Well, I'd like to start with a rather general variety whose F rational points we'd like to understand, describe in some way. And as usual, we would like to use this inclusion into the adelic point because, as indicated earlier, this is usually an easier set to understand. We're going to define, so understand this as a subset of the adelic points, but because as maybe I didn't state this so clearly before, the cost of studying this easier set is that it's harder to understand how this is inside it. But now what we'd like to do is define a reciprocity map to some more complicated target now, possibly, in such a way that the reciprocity map. So this is a target. I'm not saying what kind of a target it is, but in any case, I wanted to have some base point so that the reciprocity map being equal to the inverse image of that base point becomes a defining equation for the global point, or a rather general classification. So this would be goal of.
Defining equation means it's satisfied, but not necessarily exactly.
It's not necessarily exact, but there are, depending on the variety, I do expect it to be exact as well. Yeah? But you're right that in general, of course, it won't be exact. But nevertheless, it should give us quite a bit of refined information about the way this sits inside in all cases. Yeah, so I've been thinking about this kind of problem for quite a few years and made some progress. So for the remaining time, I'd like to describe a little bit of the progress that's been made. So you'll notice the difference between the slides was that there was a question mark here, and the question mark has been removed now. Right? Well, this describe a kind of non-abelian reciprocity law that works in a number of different situations, except it's inspired by where you're going to use this theory of arithmetic fundamental groups. So this is where fundamental groups comes into the picture yet again. But in order to avoid technicalities, I'm not going to give you a precise definition of what these arithmetic fundamental groups are, but just try to sketch the way in which they arise in reciprocity laws. And as I get to that, because the slides get a little bit more technical, maybe I'll start by showing you some more picture of the people that have inspired me in this research. Who are the originators of the main ideas that go into this reciprocity. Of course, first of all, this picture of Bldg. This picture is almost like something from a film, right? So Bldg, sorry? I don't know. It looks fairly recent, of course, in the picture. This appears in that German website. I forgot what it was called. Sorry? Maybe somebody knows. Some Stiftung website. But anyway, so Bldg, of course, defines these arithmetic fundamental groups. He set up the correct categorical framework that was necessary to generalize the theory of fundamental groups from topological spaces to more complicated topological spaces, so-called Bldg topologies. And furthermore, so he did that in the 1960s, but then in the 1980s, in a series of mysterious publications, he also indicated how we should use these fundamental groups in diverse ways, including trying to use it to study solutions to equations, which is and then, of course, another person, since I'm here in Kyoto, that I wanted to actually mention is Professor Ihara. He really pioneered a lot of the detailed study of arithmetic fundamental groups in the 1980s and 1990s, studying in particular, coming up with many very interesting and deep formulas involving the action of Galois groups on fundamental groups. And these papers have been very influential in my own thinking as well. Then here is a picture of Professor Mochizuki, who is, of course, now developing a good deal of the theory of arithmetic fundamental groups. And I'll mention some of his specific influences towards the end of the lecture. And, I can't not mention our host, Professor Tamagawa. Well, you see, the problem is that, as you know, Professor Tamagawa is a very modest man, so it's very hard to find pictures of him on the internet. But after considerable searching, I finally located this.
My memory is correct. Mochizuki's birth year is 69.
Oh, is that right? Yeah, I may have got that wrong as well. But this birth year is correct. But anyway, because he was disguised, it was quite hard to find. So anyway, so these are some of the people who really inspired my research into Diophantine non-abelian reciprocity laws. Okay, so let me describe how this law goes now. And in order to make ideas concrete, I'm going to start with a smooth projective curve over a number field with genus at least 2. Now, one doesn't have to do this. These ideas work in greater generality, in particular for affine curves and even higher dimensional things, as long as you make suitable assumption about the fundamental growth. But nevertheless, I'm going to be set it up in a rather definite context today. And denote by delta this so-called profinite étale fundamental growth of X considered as a variety over F bar, which is going to be. So I'll just give you a slightly dishonest description of what it is. What you can do is you can just take the complex points of this variety, which will then be a complex manifold or Riemann surface, and then take the profinite completion of the topological fundamental group, the inverse limit of all the finite quotients of the topological fundamental group. But once you take this profinite completion, because of the fact that this variety itself and the base point were defined over F, it turns out that this profinite completion has an action of the Galois group over F. And for this, you need a different description of the fundamental group rather than via this topological one. Nevertheless, I'll cheat and just use this quick definition. And delta n denotes the lower central series of this group. So superscript n will be the lower central series, and subscript n will be quotient modulo the lower central series. And T sub n denotes this successive quotient. So these will be then abelian groups. They're finally generated abelian. Free, topologically finally generated abelian groups. So this is just notation. Now described a version of non-abelian class field theory for X. So what this does is, what the theory does, it takes the adelic points of X and puts on it a filtration. So the indexing is that the first subscript 1 refers to the whole thing that contains the subscript. The level 2 of the filtration is a subset, level 3 is the next subset, and so forth. And then, from these things, we define a sequence of reciprocity maps now. From the nth level, it goes to a set which actually is an abelian group, although the abelian group structure isn't that important. It's important to think it's set. But they're all different for each different n. You get a different group for the different n's. And they're defined in such a way that the n plus first level of this filtration is the kernel of the nth reciprocity. So I'll put this together as a diagram like this. So the first reciprocity map is defined on all the adelic points. The second reciprocity map is defined on the kernel of the first reciprocity map. The third reciprocity map is defined on the kernel of the previous two and so forth. So it goes, progresses in this fashion. What are the targets of this reciprocity? Well, I'll just give you a very quick description. What you do is you take this nth level of the filtration on the profinite fundamental group of X, and then you take this, I guess you call this the Tate dual or something, and consider Galois cohomology of the Galois group of F bar over F with coefficients in this group, and then take the dual again, Pontryagin dual. If you do that, you get a profinite group. Sorry? Sorry. This is the group of mth roots of unity. But I denote it by mu m to denote that it has a Galois action. So everything inside has a Galois action. So that you take this Galois cohomology with coefficients in this group, then take the Pontryagin dual of that. So you get a profinite group. This is the target of the nth reciprocity. So, for example, if X is just a GM, in that case, what happens is that this target, script Gn, is 0 for n at least 2. Except for the first one, they're all 0. And the reciprocity map can be identified with the usual reciprocity map. But if the fundamental group is non-abelian, then these will all, in general, be non-trivial. Now, it's natural to put as X sub infinity, the intersection of the kernel of all the reciprocity maps. So if you define X sub infinity that way, then the non-abelian reciprocity law says that in fact the global points are inside this X sub infinity. So in other words, the global points are killed by all the reciprocity maps. So this is kind of a rather complicated sounding, but I think natural generalization of Artin reciprocity. Except now we're doing it for a curve of higher G naught rather than G. Okay, so that's more or less the whole theorem. I don't have that much more to say, but I thought I'd show you a few examples to illustrate what you get out of this theorem. Well, So here's a very brief side remark. The reciprocity often by itself often implies the finiteness of the global points. That is to say, these are all different versions of the theorem of Falkings, often follows automatically from the reciprocity. Not always, because somehow I still need to struggle with Galois cohomology in general. But situations where Galois cohomology can be more or less understood, you often get finiteness of the points from the reciprocity law. For example, for these generalized Fermat equations, you get finiteness of points just as a consequence of the reciprocity law. But that's somehow not the main focus of what I've been thinking about. Instead, you see, rather, I would like to use this reciprocity law to compute points. That's the main motivation. So just the finiteness by itself isn't that interesting, but rather what concrete one can get out of this is what I've been focusing on. So I'm going to state a conjecture here that in some sense states that the points can be computed. So how does this conjecture go? Well, in order to do that, it's inconvenient to use all the adelic points. Instead, I'm going to project it to one of the non-Archimedean components, the v-adic components of that some v. Then denote by xfv sub n simply the projection of the nth level filtration on the adel. So this way you get a filtration of the v-adic points as well. So xfv sub 1, xv sub 2, and so forth. Right? And these will all contain the infinity level filtration on the v-adic points as well, right? Intersecting with all the previous things. And the previous reciprocity law says that this guy will contain also the global points, which can be viewed as simply sitting inside the v-adic points of the world. So here, because this is just a single non-Archimedean field, there are more analytic techniques available. So here's a conjecture. So let's let X be a smooth projective curve of genus at least 2. And here I can only make the confident way to make the conjecture when F equals Q. So I restrict it to the case over Q. Then for any prime of good reduction, in fact, this infinite level of the filtration should be equal to the Q, to the Q rational point. So there's a, I'm not going to describe this, but this is, I'm not going to say any detail about this, but this conjecture is essentially this non-abelian analog of the finiteness of the tetra-Kravich group for elliptic curves in the version conjecture. Of course, the idea is that somehow this thing here should be computable, allowing us to compute the rational point, provided this conjecture is true. And the general idea, to sketch very briefly, is that whenever we have a Galois cohomology class, here I'm being very sloppy. You need various restricted ramification and so forth to make these statements precise. But roughly speaking, if you have a Galois cohomology class with coefficients in one of these dual modules, then what you do is, by this class can be regarded as a function on this Galois cohomology, so that if you compose it with the reciprocity law, you get a function on the adels that kill the rational points. You can do, and if you can compute the projection to the p-adic points in some suitable way, that is to say, you have to take this abstract reciprocity law, take one of these functions, and be able to compute this function in some concrete way via an explicit reciprocity law. And then get out of that p-adic analytic functions for zero set, cut out this nth level of differentiation. And sometimes this can be done, but this is a very difficult problem in general that I'm still struggling with. But nevertheless, here are some examples in short time. Unfortunately, the examples I can easily show you today are affine versions rather than the compact versions, but I'm going to do that anyway because that's really interesting. So when you're trying to do this for affine curves rather than compact curves, you have to replace all the rational points by integral points. And then the story goes through in exactly the same way. So here are some examples. Suppose you take x to be pure minus 3 points. This is sort of the first hyperbolic curve people have done a lot about concerning fundamental growth. In this case, of course, the global integral points is just empty. So this isn't a case where we're actually interested in computing integral points, but at least as a test case for the conjecture, it's interesting to look at this case. So here, if you compute the first non-trivial level of the filtration, the second level of the filtration, on the p-adic points of p1 minus 3 points, what you get is you just get those points where the log is 0 and log 1 minus z is 0. This is just the second level of the filtration. So this is quite straightforward consequence of a little bit of p-adic Hodge theory. Yes. Now, so of course, so the statement is that the empty set is, of course, contained inside here. And this isn't quite always empty, but sometimes it's empty already, you see, because if you look at this common zero set, Z has to be either a sixth root of unity or the inverse of a sixth root of unity. So for example, if P is 3 or congruent to 2 mod 3, then in fact, the second level of the filtration is already empty. So that the conjecture is true at level 2. For those P's. Now, when P is 1 mod 3, this actually is not, the p-adic points of P1 minus 3 points actually does contain a sixth root of unity, so this isn't quite empty yet, so you have to go to a higher level to see if to verify the conjecture. So, but then, if you compute the one higher level of the filtration, what you find is the common zero set of log z, log 1 minus z, and this so-called p-adic dilog function. That's what you get as the next level of the filtration. I'm not telling you where any of these formulas come from. I'm just saying vaguely, as I said before, they all come from p-adic Hodge theory. I'm suppressing in this discussion entirely. So in this case, to check whether the conjecture is true, all you have to check is whether this dialog vanishes at the sixth root of unity or not, right? And I've been told by many experts that this should not vanish ever. Yeah? But it seems to be very hard to prove a statement of this. So maybe somebody here can prove it. But I haven't been able to say anything of this. So it seems to be conjectured to be true by people working on p-adic regulators. But numerically, we've checked this for at least a small range of P. I don't know anything about what kind of computations are actually involved, so I'm just citing my collaborators. But they tell me that actually this computation gets very laborious as P increases, so we haven't done more than a small range of P's checking this. But so far, the conjecture appears to be numerically true for a large number of P's, well, or a small number of P's, depending on the calculation. So here's another example. So let's take X to be semi-stable, the complement of the origin inside a semi-stable elliptic curve. And here, to make things simple, I'm going to take E to be of rank 0. And the P part of the Tate-Shafarevich group should be finite. So here we get some p-adic analytic functions by taking the p-adic log. And in that case, this case, as for the P1 minus 3 point, if you compute the second level of the filtration given by the reciprocity law, it again turns out to be just those points where the log is 0. So this is just the p-adic torsion of the elliptic curve minus the origin. Now for small p, it often happens frequently that the local torsion is equal to the global torsion, in which case, in fact, the global integral points will become equal to this second level of the filtration. But of course, this fails as p grows. So you have to now look one further down in the filtration. For that, we need one other function, this elliptic version of the elliptic dilogarithm. It's an iterated integral. And we need a little bit more notation that I'm not going to bother you with too much right now because I'm out of time. So we let S be the set of primes of bad reduction, and then for each prime of bad reduction, N sub L denotes the order of the discriminant. And I get a set of numbers for each L that I'm going to denote W sub L, which end up being a kind of possible set of values for some p-adic height. But anyways. Then, once you choose a set of numbers, W sub L, for each prime of bad reduction, then I'll just denote by W with this norm symbol around it, the sum of all the WLs. So here's a theorem. Suppose E has rank 0, suppose that all the previous hypotheses are satisfied, that is, in that case, the third level of the filtration given by the reciprocity law is computed like this. It's a union of zero sets of p-adic analytic functions, where psi w consists of those p-adic points where the log is 0 and the dilog of z is equal to the norm of w. You take the union of all of those values over all w, and that's the third level of the filtration. So of course, the integral points are contained inside here, but the latter in general could be made up of, potentially be made up of a large number of sets of psi w, so it could be much larger. So one needs to check what the discrepancy actually is. But by the way, the fact that the integral points are contained inside here is already a fairly interesting explicit non-abelian reciprocity law. It's not so obvious at all from a classical point of view. So, for example, we checked it for this curve that where there are separate techniques to find completely the integral points on this curve. It is a complete set of integral points. And in that case, we first checked that in fact this is equal to the third level of the filtration. This case is relatively easy because the Tamagawa number ends up being 1 at all p. So in that case, the equation simplify, and it's easy to check this equality for at least this range of p's. And so far, so to put it simply, so far we found with our assumptions that the global integral points is equal to the third level of the filtration for all the semi-stable elliptic curves and primes that we've tested so far. So for example, for prime p equals 5 and 256 semi-stable elliptic curves of rank 0, we've checked this numerically with the theorem. So here's a list of from Cremona's table. So for example, for this curve, there's actually a large number of these psi w, 384 of them. And each of them could potentially contain some points contradicting the conjecture. But so this is the curve. And we checked all the 384 of the psi w and figured out, in fact, eventually computed that they're all empty except 4 that contain these integral points. So that was actually a very pleasant computation to do. So this is the flavor of the general examples that one hopes to generalize substantially further through better techniques for coming up with these explicit reciprocities. Now I had a number of other things to say, in particular more examples and comparison with the Langlands reciprocity, but I'll skip all that because we're out of time. And just mention briefly that somehow I tricked you and changed topics in the middle. I said that we were mostly interested in arithmetic field, then we turned it into a question of studying equations, right? Well, you see, there is a point of view whereby the studying the equations itself is the study of the field, and I rather like this point of view a great deal these days. So in particular, we can view the non-abelian reciprocity law that I stated as simply being really a reciprocity law for the field f with coefficients in the curve x. Here, we're just changing the coefficient for the reciprocity law, generalizing the usual coefficient gm that goes into the abelian reciprocity. So here, x really is a tool in some sense. We can view x as being a tool for studying f. It just allows us to formulate different reciprocity laws that give us information. This is a point of view I like very much these days, and that I really learned a lot. This kind of general philosophy, of course, I think strongly influenced on the physics. So I just mentioned that and finish for today. Thank you very much.
So, are there any questions or comments?
Your conjecture,
Right.
you detected them all. So
Right.
intersection,
Right.
the calculations you showed, it was level 2 or level 3. And
That's right. That's right, yeah.
Effect or no, then it should stabilize.
Yeah, it has to stabilize, essentially. That provided some other standard conjecture that I can't prove in general is true. What happens is that as soon as that inclusion is a proper inclusion, that x qp sub n is actually finite. So there's no choice about this method. So that's why I'm reasonably confident about the conjecture. The fact that the inclusion is eventually proper is supported by some theorems, some numerical evidence, and so many standard conjectures from the theory of motives that it's hard not to believe. But as soon as the inclusion is proper, it's finite. So then, after that, it's always the inclusion of finite sets as you go down the levels, right? So the general idea is that nothing can keep remaining in this sequence of non-decreasing sequence of finite sets unless it has a very good reason to remain there, which is that it's actually a global ratio.
Any other questions or comments? So I have two questions, one big and one technical. The first question is, you mentioned that the non-abelian reciprocity map should be viewed as a sort of tangential, sort of base point. Could you have some explanation about this?
Oh, no, I think what I said was, right, let's go back to the, right, where you were at.
Yes.
Yeah,
Yes, the next page.
that's right. So I said that,
Reciprocity is equal based.
so no, what I said is that the reciprocity map being equal to the base point of this target should be a defining equation for XF. So remember, the abelian reciprocity law says that GMF is in the kernel of the reciprocity map, right? So I'm just replacing the kernel by the statement that the reciprocity map hits the base point. Yeah, sorry. That's right. I just meant the kernel. Yeah.
Another question is related to your joint work with Stefan and others on the integer points.
Right.
P minus 3 points.
Right.
And then the third filtration is involved with the
Right,
involved
we go
space.
forward again.
With dilogarithm.
That's right, yeah.
But why the dilogarithm of 1 minus z does not appear?
Oh, why does...
In fact, it should have some symmetry.
So that's a very good point. That's because I simplified slightly. Yeah, that's right. So yeah, well, I lied somewhat. Yeah, sorry. Yeah, thank you for pointing that out. In the dilogarithm of 1 minus, that should also appear if you use the full nilpotent fundamental growth. But actually, I used the simplified version, this quotient of the lean that only takes into one side into account. You're right, actually. So that should actually improve this picture as well. I was working with a simplified fundamental.
So let's speak again.